Welcome back, everyone. In this video, we will be exploring another transfer learning architecture, popularly known as the ResNet. We will explore what it is, its inspiration, its design, and finally compare and contrast it to the VGG and Inception networks. So, let's begin. ResNet architecture was developed by researchers at Microsoft in 2015. The name ResNet comes from residual networks, which are an integral part of the architecture design. The motivation behind the architecture was the team's observation that deep networks suffer from a vanishing or exploding gradient problem, as well as a degradation problem. As we discussed before, the vanishing gradient problem occurs when the gradients that are used to update the weights and biases become extremely small as they propagate backward through multiple layers. Conversely, the exploding gradient problem happens when gradients grow exponentially during backpropagation. It was observed by the team that while the vanishing or exploding gradient problem can be solved to a large extent by using normalization layers, the degradation problem was much more trickier. What is the degradation problem? Well, the degradation problem refers to the fact that on going deeper, first, the model's performance plateaus, and then starts decreasing as more and more layers are added. For example, if you were to take a 10-layer model and add 10 identity layers to it at the end, the error in the newer model would be the same or worse. The team attributed this not to overfitting, but to the fact that the current optimizers are not great at creating an identity function using multiple nonlinear functions. The team proposed and showed that the degradation problem could be solved by using residual networks, allowing them to go deeper and create models with superior performance. A residual network is a network with shortcut or skip connections. More concretely, in this network, an alternate input connection skips the stacked layers, which could be 2 or 3, and is added element-wise to the output of the stacked layers, followed by the activation function. This is illustrated in this image of the residual network module, which has 3 convolution layers. What's special here is the addition of a shortcut, the long connection on the left, that skips one or more layers and directly connects the input to the output. The input and the output of the convolution layers are added element-wise channel by channel before being sent through the activation function, which here is ReLU. Thus, instead of aiming to learn an underlying mapping directly, these stacked convolution layers actually learn the residual functions with respect to the layer inputs, hence the term residual network. Taking our example again, if we wanted to create an identity mapping, like before, the weights of the stacked convolution layers could simply go to 0, a much simpler process than to create multiple nonlinear values that combine to become 1. In practice, this design allows you to stack many more layers in a network without suffering from the degradation problem. Each module has an input that directly connects to its output, stabilizing the training process by preserving the identity of the input through the layers and mitigating the risk of these problems. A point to note here is that when performing element-wise addition of input and stacked output, dimensions must be the same. If they are not same, either zero padding or an advanced technique known as projection shortcuts could be used to increase dimension. The paper found that projection shortcuts gave better result than zero padding. Let's now look at the complete ResNet architecture. As can be seen, it's pretty straightforward as well. It starts with a convolution and pooling layers and then stacks the ResNet modules, one after the other. The architecture finally finishes off with a pooling and a dense layer at the end for classification. Finally, let's see how ResNet differs from architectures like VGG and Inception. VGG uses a straightforward stack of convolutional layers with increasing depth, focusing on using small receptive fields or filters. It's simpler but can get quite demanding in terms of computation as depth increases without the efficiencies introduced by residual connections. Inception models incorporate multiple kernel sizes in parallel within the same network depth. This allows for more complex features extraction and higher efficiency, but introduces complexity in design and higher computational costs. On the other hand, ResNet's architecture allows it to scale much deeper than previous architectures with less complexity and better usage of resources through its novel use of shortcuts, facilitating deeper networks that are easier to optimize. They also generally offer better performance just due to sheer number of layers, which help them learn more and more complex features. To wrap up, the introduction of residuals in ResNet advanced the field of machine learning and computer vision significantly, allowing for deeper networks with increased accuracy and efficiency, and by addressing many of the core issues seen in earlier deep neural architectures. And so, whether you're dealing with a few layers or hundreds, understanding the underlying behaviors of networks like ResNet can help in building more effective solutions, not just in image classification, but across numerous other applications in AI. And that is all for this video on ResNet. In the next video, we will see how to build a ResNet model for ourselves using Python. So, see you there.